Okay, so about a week ago, I taped up some petri dishes after filling them with some pieces of paper towel, some mung bean sprouts, and some water of differing salinities. Um, I as I was kind of like aiming for a specific outcome, and we're taking off the masking tape today. And we're going to open up these petri dishes to see if we got the outcome that I was expecting. um, First, I'd like to explain a little concept, something that farmers struggle with. It's called salinization. Um, Salts are often found in water. So, rocks are made of minerals, and minerals will often dissolve into water as water pours over the ground. Here in Santa Barbara, we have a lot of groundwater. So when you take that water out of the ground, it'll have a lot of dissolved minerals in it. Because, it was in the ground and there's rocks in the ground. So here in the man cave where I'm recording this lecture, I wrap fishing rods. You may know that I'm a fisherman and I like to make my own fishing rods. Maybe we've talked about this. And every couple of weeks, I need to refill this like water bath for my epoxy. So I have two-stage epoxy that I use to cover up the wraps on the guides for my fishing rods. If you're ever interested, I can show you. It's interesting. And so I go into the kitchen and I grab a bunch of water, and then I come here into the man cave and I use that water to top off this machine I have over here that puts my epoxy into a water bath, so it'll be at like 80 degrees, and then I pump out the epoxy and I do my fishing rod thing. But I always get like a full thing of water and I end up using a little bit less than a full bottle. And so maybe you've noticed this, that when water is left to evaporate, salt is left behind. Those are minerals. That's mineral buildup in there. Maybe you can see that. It's, like if this was a glass that I wanted to drink out of, I would probably clean this because people find it, less appetizing when they can see all these mineral deposits. But mineral water is actually good for you. These are useful in your blood because your cells need dissolved minerals sometimes. But imagine if you're a farmer and you're using Santa Barbara tap water and you water your garden, and some of that water will flow down into the ground, but some of that water will evaporate, leaving some of this mineral on the soil. These are salts. And over time, when you water and it evaporates, and then you water and it evaporates, and you water and it evaporates, salts can build up. That's called salinization. It's especially bad if you use a lot of groundwater, like we do in Santa Barbara. You should write this down, groundwater. It's especially bad if you're farming in the desert, where evaporation is a bigger problem. It's especially bad if you're in a basin, because the water pours in, but it can only leave through evaporation. It can't run off in any other way. And in the Green Revolution, 1970s, we started to use a lot of fancy chemistry, interesting stuff that we can add to water, like fertilizers. And of course, when that water evaporates, maybe there's extra stuff left behind. Coincidentally, some pesticides also leave mineralization or salts behind. And what can eventually happen is that a farmer might have so many additions of mineral with repeated evaporation that they start to build a crust like this in their soil. And if it gets too salty, it can affect the growth of plants. This is a process called salinization. It's nothing new. The Egyptians dealt with this. And the accumulation of salts is perfectly natural. You might know that the ocean has a lot of salt in it, right? Because water pours in and can only leave through evaporation, so that salt is left behind. That's why the ocean becomes saltier. Fun fact, that's the difference between a lake and an ocean. Cool detail that young people never really are led to. A lake has an outlet. So water goes in with some dissolved salts, but that water exits because the lake has an outlet, an exit. So lakes do not become salty. But ocean is the low point. Water pours in and cannot leave unless it's evaporating. So the salt, once it arrives, has no place to go because salt does not evaporate, right? When the water evaporates, the salt is left behind. So the ocean, like my glass, has inputs of water that evaporate, but the salt is left behind and it accumulates like in my glass. You know, I use this thing every couple of weeks. I haven't washed this glass in probably 3 or 4 years. It's just like in the man cave. It's what I do. I go outside, get a little bit out of the hose, come inside, fill up the thing with water, and then whatever's left just keeps on evaporating. So if you ever hear of a lake that is salty, it's not actually a lake. Like the Great Salt Lake in Utah, that ain't no lake. That's an inland sea. Maybe you've heard of the Salton Sea. That's named correctly because it's very salty. It doesn't have an outlet. And so it is indeed a sea. It's called the Salton Sea. It's not a lake. You can tell because it's got salt. There's a place up in the Sierra where I spend a lot of my time. In this picture, it would be in that direction. In this picture, there's a place called Mono Lake. It's north of Mammoth. Maybe you've been there if you ever drive to Bridgeport or Tahoe on the 395 corridor. If you've ever been to Reno and you go up the Eastern Sierra, you've seen Mono Lake. That ain't no lake. It's salty. Water comes in with salts. The only way for the water to leave is through evaporation, so the salt is left behind and accumulates, becomes saltier. Seas accumulate salt. So likewise, imagine if you're a farmer in a basin and water comes in but has no way to drain out, then because you're farming in a basin, you're going to get saltier and saltier soil, you know, like a salt flat or a salt lake. This is a really big whoop for Israel. Israel is in a desert using a lot of groundwater. There's coastal mountains that kind of surround most of Israel's farmland, and you know, evaporation is a big problem. So they take groundwater, they irrigate an arid basin to grow food, and their soil is becoming so salty that it's become really difficult to grow their food. Now, here's the proof for you. I hope you can see. This is the 0%. I don't know if this camera flips or not. So here's the 0%. And if I take off the paper towel on top, I've got 100% sprouts. All 10 have sprouted. 1, 2, 3, 4, 5, 6, 7. Yeah. Big old sprouts. This is mung bean. If you wait another 2 or 3 days, these will be big enough to put into stir fry or like spring rolls. So the 0% had perfect 10 out of 10 germination. Just saying, I kind of expected this to happen. Here's the 0.5. You'll have to forgive me. I really don't know if my screen is going to flip or not. So I'm trying to show it both ways. 0.5. Here's the lid for it. You know, fun fact, these are really, really stinky. When we do this in my classroom, people complain about it for like a week. The smell in my room is grotesque. It smells really bad. So here, this is really gross, and like I'm grossing myself out. So I'm going to pause this video as soon as I'm done showing you these results, because I need to go wash my hands because it's really gross. Okay. That's 10 out of 10, but you'll notice these are a little bit shorter. If I go to the 1%, here's the 1%. Now this is interesting. These have sprouted, right? I call it a sprout if you can see a little root coming out. But you'll notice that they're not really getting this far. If you know physics and chemistry, osmotic pressure, it's harder for the water to push tissue out of the root because it's too salty. So the water's struggling to get out. I would say this is 8 out of 10 because a couple of these don't have a visible root. Maybe 9, actually. Yeah, maybe 9 out of 10. This one has like a teeny bit of a root, but it's barely visible. So in the 1%, we have a little decline in germination, maybe 90%, 80%. It's kind of tough to be sure. Now, when I go to the 1.5, my hunch is, because I've done this lab a lot, that we're going to see some decrease in germination. Oh, this one smells really bad. And we do see a very significant decrease in germination. There's like 2 or 3 that have a little tiny piece of root coming out, but just barely. Like that guy has a little bit of root coming out. This one in the front of my finger, that one has a teeny bit of root coming out. But these, the 1.5, I'd say maybe 20% germination. And please don't make me do it because I already know what's going to happen. These smell really bad. And when I step up to like the 2%, I can't even show you this, but anyway, 2%, we've got, oh, one of them germinated. Kind of a surprise. One germinated here. 2.5, 3, and 3.5, they're just rotten. Nothing happened. So 2.5. Ooh, this smells really bad. This is horrific. Ooh, I just dropped some on my space heater, which I'm actually using right now. So yeah, the 2.5 is barely cracking the skin on the seeds, no germination. 3. Smells really bad. It's moldy. And they've, kind of cracked the skin a few times, but there's no roots coming out. 3.5. Fly got into my man cave today, and it's really annoying me. I hope you can't hear it on the microphone. It's like a big old fly, and it's really loud. I left my man cave closed down for the day because I was cleaning the yard. So those flies had the run of the place. Oh man. Okay, so these didn't even crack the skin. It's 3.5. This is kind of the result that I expected to see. Look, I'll prove it. In previous years, I would gather my results from all of my classes, and at the end of the day, we would compare the results of all the lab groups. And I'll show you. The last time I was in the classroom, this is what my students came up with. You can see that they're color coded. So all the green dots were lab groups in period 1. All the purple dots were lab groups in period 2. I just did this spontaneously on the whiteboard while the students were reporting their data to me. So I'd be up in the front and they'd say, we got, and we have a lot of repetition, right? This is a lot of data samples. So when you do an experiment, you want to run a whole bunch of data samples, right? So that you're not confused by one weird event. So here's all the 0% salt water. And you can see they had nearly 100% germination. All the 0.5 was mostly 100%. All the 1.0 was mostly about 92, 93 is what I would say is the average of all of them. At 1.5, there was a bunch of zeros and a couple of 10%. The class average that year was about 35% germination at 1.5. And then by 2, 2.5, 3, and 3.5, the levels get really low again. Now, here's what happens. Plants cannot grow when soil is really salty. As a matter of fact, seeds cannot sprout successfully after about 1.6, 1.7. In this diagram, in this diagram, we'd say the tipping point, the halfway point, is at about, look at this, about 1.4% salt. There's a reason we're talking about this. I hope you're writing things down. You can see hydrogenation, starting to see a little impact, but the tipping point, the halfway mark, the number where things go from mostly good to mostly bad, the 50% line is at 1.4% salt water. Now, the reason we go all the way to 3.5 is that's the ocean. And we know that you can't grow stuff with ocean water. But as a matter of fact, you can't really grow stuff with half ocean water. You got to be below that. You got to be at 1.4 to have at least a 50-50 chance of germinating seeds. Today, farmers have to be really careful. They have to, you should write this down, they have to avoid salt in their irrigation water. They have to limit agricultural chemicals because those also bring salt into their irrigation water. Today, farmers need to flood their fields sometimes, make the ocean into a lake, right? If I fill this up with water, stir it around so that all the salt has dissolved, and then I pour it out, I'll have less salt left because I've let the salt leave once it dissolved. So in a farm, what farmers can do is they can just flood the field. And because there's so much water, all the salts will dissolve. And then if you let that water out somehow, by the way, that's the old school way. That's how the Egyptians handled this. I told you that the Egyptians dealt with salinization, right? So the way that they dealt with this is they would intentionally have their farms in a floodplain so that occasionally a big storm would wash away their salts. As a matter of fact, they used to dam the river off, right? So that they could bring water in under controlled conditions. But when it got really salty, they would lower that protection. They would like take away a mud or rock dam and let the river wash over the farm to take away the salts. That's the traditional way to deal with this. We use desalination, reverse osmosis, but fun fact, this is why a lot of farmers fight for water from melted snow instead of using groundwater. Because if they use a lot of groundwater, they can accumulate all the salts that are in that rocky deposit, right? So a lot of farmers will fight for access to high elevation water, like the stuff that's falling on my children. That's just rain, barely touches rocks before it reaches the farmer, as opposed to water that's soaked into the ground and been in touch with rocks for tens of thousands of years. Then when you bring up that groundwater, that's got a whole lot of mineralization. So limit salts, avoid groundwater, avoid agricultural chemicals, and whenever possible, flood to get the salts out. I got to make sure. You've watched the experiment video. You know why salinization happens. Dissolved minerals are left behind when water evaporates. Reverse and write that down. It causes stunted growth and decreasing germination, and it can be avoided by avoiding salt in your irrigation water, limiting groundwater, occasional flooding, and limiting agricultural chemicals. If you just let the rain fall on your plants, you don't really get a lot of salt being added. Okay, I'm sorry that you couldn't do this lab yourself, although you might not be sorry. I had to deal with this smell, and by the way, it's been pretty smelly in my man cave for a few days now, and it'll probably stay smelly for a few more days. Thanks for watching the video. I guess we're all good. I gotta figure out how to stop this video because I've changed my screen. Okay, see you in class.